All right, dude, we are live for the second time today. We are back again, and we're gonna continue doing what we were doing. I had to just just as a bit of a recap, we got done reading the. Do I still have that open? I don't know if I still have that open. I don't wanna load that up again. But we got done reading the underfitting and overfitting section of uh, of the chapter of the course. We got done reading the theory of the underfitting and overfitting section, and now we are doing the exercise portion of it. That's why I've loaded up this notebook. The reason I said I don't want to load that other page is because I don't know if that's going to cause some kind of instability. Right now things are working, so I would rather just finish this exercise as soon as possible. Which I don't think this is going to be a very long exercise because yeah, no, I'm interested in seeing what kinds of challenges this specific exercise brings in. Okay, recap. You've built your first model, and now it's time to optimize the size of of the tree to make better predictions. Run this cell to set up your code to set up your coding environment where the previous step left off. Oh, this is the entire. Okay, all right. Which data set is it using? Home. Which data set was home? Oh, this time it's using Iowa. Okay, all right, fine. Um, This time it's using Iowa, so let's move this over. Yeah, I mean, I don't need to do this. We've already done this practically, so it's okay. But I'm gonna do it here anyways. Give me a second. Okay. Right. So what is this doing? It's loading the well, this is the path, and then here it's reading the CSV file and loading the data set, and then here it's loading the sale price column. So this is our target variable. These are the feature names. Here it is using the feature names to pull the only the features that it needs. So then all of those columns are going to be stored in here. So this is going to be our features data set. And then using that, we split this into our training and validation sets for both X and Y. Right. Have has all of that been done? Yeah, I think all of that has been done. Okay. Okay. Then oh yeah, so I think something that I'm noticing, and I don't know if this has been happening with the other chapters or if it just started happening, but something that I noticed is that they were using in the theory section when they were showing the code, that was using the Melbourne data set. But now in the exercise section, it's using the Iowa data set. Unless I'm remembering wrong, and even in the theory section, the code was using using the Iowa data set. I think it was the Melbourne data set. So like I think in the theory they're showing the Melbourne data set, and in the practical version they're showing the Iowa data set. So like in the exercise and stuff, they're showing the Iowa data set. Either way. Um, right, so we have our Iowa model, and then we fit, and then we predict. Uh, yeah, I also need to do the mean absolute error thing. So, where am I storing this? Right, so we have our prediction, and then we create val may equals mean absolute error with our true. Right, I need to keep reminding myself that first comes true and then comes the actual prediction, pred. Okay, and then we print out the validation. No, the validation. No. We print out the error. First in sample predictions and then actual target values. Actual target values would be very long, so maybe let's not print more than just the head. And then let's do, yeah, let's just print, yeah, let's just print this. Val may. So we are going to, wait, is there an error? No, there's no error. Okay. So we're going to run this and see the result. There's an error. Found input variables inconsistent. Wait, what line is this on? Wait, I'm a bit confused by this because this is not pointing to anything in my code. Wait, let's try that again. Uh, this this is not giving me a specific. Hold on. Validation, regression. Yeah, but where is the error occurring? It's not telling me that. Okay, let me just read my code and make sure. Val and pred. Oh, this might be the issue. This might be the issue. Okay, it's not the issue, but hold on just a second here. Dude, it is not it's not giving me a line number. Okay, it's saying found input variables with inconsistent number of samples. Okay, let's do something here. Okay, for the sake of debugging, let's do that. Okay, that ran. Okay, okay. So the error is here. Okay. Oh, I think I'm supposed to be giving it just Y because wait a second. I just realized something. Uh, this is so dumb. Okay, I did the split, but I didn't use any of them. Like, yeah, I didn't use the thing. So val x, and then we use val y here. Now we should be fine. Hopefully, I think. Yeah, okay. Yeah, that was my mistake. Okay. Um, Now let's print. Okay. All right. So now let's also run this. Actually, in the meantime, while I was doing my thing, I could have run this cell and things would have been a little bit faster. Anyways, let this run and okay. Once this is done running, we'll be continuing with this anyway, so we can move on with this. So you could write the function get may yourself. For now, we'll supply it. Yeah, it's pretty simple, right? It's basically just this logic, but like we are making it. Wait, hold on. It's basically just this exact logic. You create the model, fit the data to the model, or fit the model with the data, or however you want to say it. You train the model on that data, um, and then you predict using new data, and then calculate the mean absolute error. Okay, so we'll run this, and then compare different tree sizes. So write a loop that tries the following values for max leaf nodes from a set of possible values. A set of possible values. Okay, all right. Call the get may function on each value in max leaf nodes. Okay, right. Let's test it out here first. So let's say max leaf nodes equals 5, 25, 50, 100, 250, and 500. Okay, then we do, I don't know, max leaf. What is, hold on, dude. Yeah, I guess that's why candidates was necessary. Candidate max leaf nodes. Fine. Max leaf nodes in candidate max leaf nodes. Um, Val may equals get may. We want to pass in max leaf nodes and basically our entire data set. So train x, train y, or val x, I think. Yeah, val x, train y, val y. Okay, print uh, max leaf nodes, max leaf nodes, and then do that tab thing. And wait, is that what they're asking us to do? Oh no, they're asking us to run this and then mention the best tree size. Okay. May is val may. All right. So then we can comment all this out and run. Okay, so once we run this, oh God, I have to write the same thing here. Okay, all right, max leaf nodes in candidate max leaf nodes. Then we do val may equals get underscore may max leaf. See, this is where it becomes a bit frustrating because due to lack of IntelliSense, I have to make sure that I type everything right. Okay, train x and then val x and then train y and then val y. Right. Um, do we, what's going on? Okay. Then print, um, okay, let's say mln is max leaf nodes. And then MAE is val underscore may. Okay, let's run this and see our result. So at 5 we are here, 25 we are here, keeps reducing, 50 we are here. It's slowly starting to like the reduction the reduction of error is slowly starting to slow down. Okay, so it seems like the best size is 100. Great. Okay, that's done. Uh, let's take a look at the hints. Okay, you will call get may in the loop. You'll need to map the names of your data structure to the names in get may. Okay, and yeah, pretty much this is what I did. Oh, hold on, dude. Is this a Oh, that's clever. They use list. They use okay. This is a dictionary comprehension. I was about to say list comprehension, but yeah, this is a dict comprehension. I've actually never done a dictionary comprehension. At least I don't think so. I've only ever done list comprehensions. That's interesting. Yeah, I should look into that as well. Because there have been situations where it would have been useful for me to be able to generate the list dynamically along with like given keys and actually there are I mean there are more verbose ways of doing it. It's just that I've never done it with a dictionary comprehension. Either way, this is what they went with. Nice two-liner. How many lines was mine? Oh, okay. Yeah, I mean it's not a whatever. It's fine. Then fit model using all data. You know the best tree size. If you were going to deploy this model in practice, you would make it even more accurate by using all of the data and keeping that tree size. That is, you don't hold out the validation data now that you've made all your modeling decisions. You don't hold out the validation data. I'm confused by what that means. You don't hold out the validation data. So does that just mean you pass in the entire data set? Now that you know the, yeah, okay. Would that, hold on, let's see what variables we have available. We have X and Y available. We're going to try that first because I think that's what they're getting at here. That, okay, let's, actually, let's test it out here first. Okay, here we can do, we still need the random state. We can do max leaf nodes equals 100, and then model.fit. For now, we can test it out with just X and Y, and then we'll predict. How are we predicting? How exactly are we predicting then? Okay, we'll use val x to predict. But because we are using val x, the prediction size should then match, I believe, with val y. How are we calculating the error? If we are working on newer data, then how are we calculating the error? We are no longer in the validation stage. How exactly are we calculating error then? Wait, let me run this and see if this runs without any issues. Okay, that seems like a that seems like a fairly low score, doesn't it? A fairly low error, I mean, doesn't it? That's 16,000. I don't think that's bad. Okay, so let's say max. You know what? Wait, let's try changing the state. Still low. Okay. Max leaf nodes equals 100. Random underscore state equals 1. And then here we want to fit x and y instead of train x and train y. Holy shit. I got that right, dude. Hell yeah. Okay. So we are officially done with this. Let's actually hold on. I want to see what, like, if they have any helpful information here. So fit the model, no, fit with the ideal value of max leaf nodes in the first step and use all of the data in the data set. Okay, yeah, so X and Y. All right, so my brain connected it in the right way that, yeah, you need to, like, you're done with the training phase. You don't need to split them into training and validation data anymore. You can just train the data, you can train the model on the entire data set. All right, dude. Great. So we just learned how to essentially tune the model. This is one of the parameters that we were able to tune. I need to dive deeper into decision trees to understand exactly how we could improve this kind of a model. Because, okay, so we have decision tree regressor. I also want to look at decision tree classifier if there is one. I don't know. Hold on. Let's check. Let's go up here. Under tree, yeah, there is a decision tree classifier. We should look into this as well. Yeah, we should definitely look into this. I'm super interested in, because dude, this can be useful for like decision making stuff if you think about it. Like you notice how there's this question and answer thing going on, that hey, okay, is this the case? Yes, then do this. No, then do that. Okay, so let's say it's a no. Now, is so and so the case? Yes, then go in that path. No, then go in that path. It's basically a bunch of like nested if else statements, right? So I can see this being useful for certain types of applications. And the best part is that we don't have to write the conditions ourselves, but I need to understand how decision tree regression works, and even classification, how decision tree classification works, in order to understand how it's asking the questions, so to speak, how it's forming this tree. Because only then will I be able to control exactly what kind of a decision making. It's actually, yeah, I just realized that it's in the name, right? Decision tree. So this can be used for decision making. Maybe I don't know about prediction, but like classification, definitely. I should look into that. Anyways, this is our, yeah, we are done here. So you've tuned this model and improved your results, but we are still using decision tree models, which are not very sophisticated by modern machine learning standards. In the next step, you will learn to use random forests to improve your models even more. Awesome. Let's start the tutorial. We are officially done with this chapter, dude. Let's go. Let me load that up. What was it? Random forests. Hell yeah, dude. Let me just make sure that we have all the data sets. Yes, we do. And this is something I'll need to do for the next thing as well, for the next course as well. I'm going to need to make sure that I have the entire I need to make sure that I have all the data sets that are required. Unfortunately, it doesn't mention all the data sets that are required here. For example, it mentions Melbourne dataset. It mentions this mobile price classification, whatever this is supposed to be. It mentions that, but it doesn't mention the Iowa dataset. But like if I run a code cell, if I open up a code cell and um, what was I saying? Yeah, if I create a new code cell and I try to list all the data sets that are within the input directory, it's going to show three data sets, not two. But like here under datasets, it only shows two datasets. So it's hard to determine exactly which all datasets are in use. But as the need arises, I can download them using the Kaggle CLI. Dude, this workflow actually works out really well for me. Learning through the Kaggle website, but then practicing it on my own machine, mainly because I have IntelliSense available there. That's why it works out much better for me. Because, dude, I remember major fatigue from, like, be it mental or physical fatigue, mostly it was mental fatigue, from having to deal with silly errors because, oh, I I missed a character in a name for a variable, or I accidentally capitalized a function's name, or I didn't use underscores in wherever whatever place required underscore. That was so frustrating that it was incredibly slow to get through these lessons. But now that I'm able to actually practice this on a separate machine, or even just practice this in a separate environment. It could all be on the same machine. I'm doing it on a different machine because that's more convenient for me, but like it could all be on the same machine as well. Now that I'm able to practice it in a separate environment that actually has IntelliSense, things are going so much more smoother for me. I can focus on learning now. Okay, so let's see what random forests is about. This seems like a very small chapter. This is a very small chapter. Holy shit, this is a tiny chapter. Though the code might not be so tiny. Actually, give me a second. Let me hydrate and then we can start. Okay, random forests. Introduction. So, okay, this first sentence is funny. Decision trees leave you with a difficult decision. A deep tree with lots of leaves will overfit because each prediction is coming from historical data from only the few houses at its leaf. But a shallow tree with few leaves will perform poorly because it fails to capture as many distinctions in the raw data. Sorry, zoned out. Okay, yeah. What was I what was I doing? What was I saying? Holy shit, I zoned out big time. I was looking at the walls in my room just now. And I have a lot of whiteboards. Like back in the day, I used to use whiteboards a lot, and I still have a bunch of them, and I still use them like to a certain extent. But my thing was that I wanted to put the whiteboards up on the wall. The issue is that putting up whiteboards on the wall requires nailing something to the wall, and that tends to be a little complicated. Um, which is why I haven't done that. And my next best thing that I thought of was either um, either painting specific areas in the wall with white paint with whiteboard paint. I forgot what the whiteboard paint is called exactly, but it's a specific kind of paint that when you paint the wall with that, then you'll be able to use a marker on the wall and then even erase it. I don't know how well that's going to work out though, because whiteboards are usually very smooth surfaces and walls are not, like, at all. Um, so I don't know how well that's going to work out for the health of the marker. Like the marker itself might, the tip of the marker might go bad over time. I don't know how well that'll work out. But the next idea that I had was to just laminate some A3 size paper and use that instead. So I could use like double sided tape or any kind of sticky tack or something to stick that laminated paper on the wall, and then I can just write on that and erase whenever I need to. Yeah, that's what I was thinking of. I'm gonna have to do that because I need to be able to visualize these things. Actually, I should see if there's a way to visualize trees in Matplotlib. I haven't tried that yet. I've tried mainly charts and plots and stuff. Anything that's graph based, I've tried that, but I haven't tried visualizing a tree. I don't know if Matplotlib can even do that. I mean, it might be able to. I'm pretty sure if Matplotlib is not able to do it, then there might be a library that's built on top of Matplotlib that is able to create these trees for us. I'm sure there must be something that can do this visualization for us. And then I might be able to visualize the decision tree's decision process. Okay, anyways, let's carry on reading this. Okay, so right, a deep tree with lots of leaves will overfit because each prediction is coming from historical data from only the few houses at its leaf. But a shallow tree with few leaves will perform poorly because it fails to capture as many distinctions in the raw data. Even today's most sophisticated modeling techniques face this tension between underfitting and overfitting. But many models have clever ideas that can lead to better performance. We'll look at the random forest as an example. The random forest uses many trees and makes a prediction by averaging the predictions of each component tree. Oh, that's interesting. Okay. So instead of one decision tree, now you make like a tree of trees, essentially. Actually, it's not even a tree of trees. No, it's a group of trees, and then you're taking the average of their answer, like what what direction their answer leans towards. You kind of go with that. It generally has much better predictive accuracy than a single decision tree, and it works well with with default parameters. If you keep modeling, you can learn more models and even better performance. But many of those are sensitive to getting the right parameters. Okay, example. You've already seen the code to load the data. You've already seen the code to load the data a few times. At the end of data loading, we have the following variables. Yep, we do. Okay. So this is where we split our data set into training and validation data. Yep, train test split. Okay, and here we are back again. Melbourne data set. Look at that. This is what I was telling you. In the theory, in the tutorial, they're using the Melbourne data set, but in the exercise, they seem to be using the Iowa data set. Oh, yeah. Where was I? Yeah, so this is our usual thing. Okay. We build a random forest model similarly to how we built a decision tree in scikit-learn, this time using random forest regressor class instead of a decision tree regressor class. Oh, okay. All right. And then let's see what it looks like. Wait, so then, hold on. So with a random forest regressor, would the random forest regressor then choose different max leaf tree or max leaf nodes parameters for each of the models? And how many trees is it generating anyways? I guess we can control that, right? And then we wouldn't need to create a get may function because um, this is essentially giving us an average of the predictions. I'm guessing that's what's happening. It's giving you an average, right? Was it mentioned somewhere here? Yeah, by averaging the predictions of each component tree. Yeah. All right. So let's try that out. Cool. Let's so from wait, no, it should be in here, right? No, I guess it's not. What is ensemble? Okay. From sklearn dot ensemble import random forest regressor. Oh, I'm interested in this. What is random trees embedding? An ensemble of totally random trees, an unsupervised transformation of the dataset to a high dimensional sparse representation. A data point is coded according to which leaf of each tree it is sorted into. Using a one-hot encoding of the leaves, this leads to a binary coding with as many ones as there are trees in the forest. Hold on, dude. There's something interesting about what I'm reading here, even though I don't fully understand what I'm. Okay, we can look into that later. Okay, what's the description for this? A random forest regressor. A random forest is a meta estimator that fits a number of decision tree regressors on various subsamples of the data set and uses averaging to improve the predictive accuracy and control overfitting. Trees in the forest use the best split strategy, i.e., equivalent to passing. Hold on. Um, Splitter equals best to the underlying sklearn tree. The subsample size is controlled with the max samples parameter if bootstrap equals true. Otherwise, the whole dataset is used to build each tree. This estimator has native support for missing values. During training, the tree grower learns at each split point whether samples are missing values. No, hold on. Whether samples with missing values should go to the left or right child. Okay, based on the potential gain. When predicting, samples with missing values are assigned to the left or right child consequently. If no missing values were encountered for a given feature during training, then samples with missing values are mapped to whichever child has the most samples. Okay. Oh God. Okay, chill out. Damn. Yeah. Um. Oh yeah. After you build the model. Right. So let's build the model. So we have our training and validation data, right? Then we create the model. So forest. Oh. What did I just do? Yeah. Forest model equals random forest regressor. And what are we providing? Random state. N estimators. So does this control the number of? I think I should look at the documentation for it. But yeah, I was about to ask you if this controls the. You know what? Wait, no, hold on. Yeah, now we can read this. Parameters N estimate the number of trees. This is what I was asking. So the number of trees in the forest. By default, it creates 100 trees. This is great because this adds a certain level of um, I don't know if noise is the right term to use here, but it adds a certain level of like generalization in there. It adds a lot of variety because it's probably splitting the data in its own way. Um, it's probably using different max leaf nodes. It's probably changing a bunch of the parameters in different ways that makes this a little better at generalizing on newer data. If that makes sense, I don't know if that makes sense, but yeah, random state equals one, and then we just have to fit it, right? We fit the model the same way, and we make our prediction the same way. Forest model dot fit train x and then train y, and then prediction equals forest model dot predict. We want to predict on val x, and then we calculate our may using val y and pred. So we then do, we just print out the, we just print out may. Are we good? I think we're good. Holy shit, dude. That's crazy. That is crazy. Right off the bat, the score is low, as in the error is low. Wait, no, no, no. Hold on. Did I save this? This is not what's supposed to be. Oh, I'm looking at the wrong one. That's funny. Now let's see. Back up. Why did that just run? Oh, okay. So the score is not as low. Um, yeah, the score is not as low in this case. Is there something that? Wait, no, no, no. Hold on. Let's move forward with what this is. Oh, even here the score wasn't that great. Yeah, even here the actually the score is pretty much the same. Oh, that's probably because of the random state that I used. Yeah, the score is pretty much the same. Okay, there's likely room for further improvement, but this is a big improvement over the best decision tree error of 250,000. Okay, there are parameters which allow you to change the performance of a random forest, much as we changed the max depth of the single decision tree. But one of the best features of random forest models is that they generally work reasonably even without tuning. Oh shit, I just realized you guys can't see this. That's okay. That's embarrassing. So this is what I was looking at. And then I'd also looked at this. This was where it had mentioned that it was using the Melbourne data set. But yeah, okay. Now we are ready to move on to the exercise, which is using a random forest model. Okay, good. So the thing isn't getting stuck. So that's good news. Give me a second. Okay, now while this is loading, okay, never mind. Let's start by um running this model selection, train test split. Okay, Iowa file path. So we need to do this here. Okay, decision tree regressor. Right. Okay. Iowa model fit. Great. Awesome. Iowa model predict. Okay. Then calculate the error. Okay. Then using the best value for max leaf nodes. Cool. Okay. Wait. Oh, yeah. Okay. This is validation may when not specifying max leaf nodes. And this one is for the best value of max leaf nodes. Let's run this. Great. That ran pretty quick. Okay, so this is what we've got. Now, use random forest. Data science isn't always this easy, but replacing the decision tree with a random forest is going to be an easy win. Yep, definitely. So, random forest regressor random underscore state equals 1. fit your model. So rf underscore model dot fit train underscore x train underscore y, then calculate the mean absolute error. I like that now it's kind of become muscle memory for me that, oh yeah, our validation, our data set has been split into, or not even muscle memory. Now it's kind of like just, I've kind of understood that concept that our data set has been split into training data and validation data. And when we are talking about the model prediction, um, y is the target variable that we are predicting, and x is the features, however many features there may be. And so because our data set is being split into training data and validation data, so there's going to be train x and train y, and then val x and val y. I don't know. That makes me happy. That tells me that I'm learning. I'm getting this. So mean absolute. Did I spell that right? Nope. Absolute error. True comes first, right? So that's val y, and then what? Calculate the mean absolute error of your random forest model on the validation data. Yeah, but you didn't run the model. Okay, let's do pred equals rf model dot predict val underscore x. Okay, and then we run this and see if that's correct. Holy shit, that's correct. And yeah, that did improve the error. I need to see if there's a way to improve the error on. Actually, okay, there's something worth noting here because I'm comparing the Melbourne dataset with the Iowa dataset, but like I also need to take into account this that hold on, print what was it called? Melb data? Yeah, melb data dot describe. Let's run this. Wait a second. Yeah, that's better. Yeah, let's run this now. So the max is the max price mentioned somewhere here? Sale price. I need to look for the sale price. Sale price. Can I do this? Or is this going to return a series? The funny thing is that at this point in time, I'm not supposed to know. At this point in time, I'm not supposed to know about accessing as series or whatever. That's supposed to come later on, which fortunately is the next chapter, actually. Um, the next course, sorry. The next chapter is a competition. The next course is, what do you call it? Pandas. The next course is pandas. Is there not a sale price here? Oh, no, it's just price, not sale price. Sale price is in the Iowa data set. Okay, let's run this again. Oh God. Okay, these numbers are so big. These numbers are so big that they're being presented as scientific notation. You know what? My point here, the reason why I was doing this thing in the first place was we achieved an error of about 100 and let's say 10 or $120,000, wasn't it? Hold on. What was the error? Uh, Save this. Oh, no, close to, let's call it 200,000, okay? Or let's say 190,000. We achieved an error of $190,000, but that is on houses that are like in the millions, if I remember right, because I believe these data sets, or the Melbourne data set does have houses that are like in really, really big amounts. I think the Iowa data sets houses might not be nearly as expensive. Um, so maybe what that's telling us is that, and that's why even I think the theory or the exercise, one of these two mentioned that being less than a quarter of a million in error is a good thing. It's not bad. Anyways, we are done with this. Let's take a look at the hint and the solution. So review your code above with the decision tree regressor. Use the random forest regressor instead. No, review the code. I was like, what do you mean review your code above? But yeah, okay. That is exactly what I did. Great. Awesome. So far, you have followed specific instructions at each step of your project. This helped learn key ideas and build your first model. But now you know enough to try things on your own. Machine learning competitions are a great way to start. Machine learning competitions are a great way to try your own ideas and learn more as you independently navigate a machine learning project. Keep going. You are ready for machine learning competition. All right, dude, this is amazing. This is amazing. Holy shit. We are on the last chapter of this course. We are 85% completed. The only chapter that remains is this. And I don't think I'm going to do this on stream, but I will finish this today. I'll finish this today and we will be officially done with Intro to Machine Learning. Dude, I'm excited. I am definitely excited. Um, Hold on. Where is, was this Kaggle Learn? Yeah, Kaggle Learn. I wanna see what the next chapter after pandas is supposed to be, because I can't remember. I think it was intermediate machine learning, because that talks about handling missing values, non-numeric values, all of that stuff. You would, a lot of times you would do that with pandas or scikit-learn. Um, and dude, feature engineering is also that's a very interesting concept that I'm excited to dive into. Okay, now hold on. Give me a second here. Okay. Okay. This is the first person that I've seen. Legit. Um, this is the first person that I saw as soon as I opened up the co-working and studying category. So I can either go with this person or I could go with somebody who's a medical student. I'm not sure what they are doing. Let's open up their stream and see. Nope, verified accounts only. Let's take a look at this person, the initial person that I was looking at. I hope it's not follower only or verified accounts or whatever. No, it's not. Okay, great, awesome. Uh, right. So this person is 45 minutes into their stream. So we're going to go hang out in their stream. Okay. I'm going to set up the raid here. Where's my stream manager? Here it is. Yeah. I'm going to set up the raid here. This is a person named Cozy Ophi. Yeah. Cool. Awesome. Let's go to Ophi's stream. That being said, dude, I'm excited. I'm excited to finally finish Intro to Machine Learning and then move forward with Pandas and Intermediate Machine Learning. Pandas, if I'm not wrong, it should go pretty quickly because I know the basics of Pandas pretty well. So it'll be more about learning the more advanced stuff for me and filling in the um, tiny but many gaps or holes of knowledge that I don't have when it comes to pandas basics. Because I know the basics, I've used pandas even in projects. I'm fairly comfortable with pandas. Pandas is one of those things that every now and then I'll need to go and Google, hey, how do I do so and so thing in it? How do I filter in a specific way, or how do I format in a specific way, or how do I change stuff in a data set and stuff like that. But for the most part, I know the basics, so it should go hopefully pretty quick. But yeah. Anyways, my raid timer is running out. So that being said, I hope you guys have a nice day, and I'll see you all next time. Peace.